Everyone, good morning. Yeah, hi. I would first like to thank NAMI for inviting me yet again for the summer school slash winter school. So I've been sort of a regular speaker here. So I think this is my fourth or maybe perhaps fifth time here. So I really enjoy coming here and interacting with all of you. So today, so just a little bit about myself. So I'm at IIT Kanpur in India, and my prime area is natural language processing. And as you all know, nowadays there is no NLP without LLMs, and that's what I'm going to talk about today. So I'm going to start this sort of a brief overview of things. Let me see if I can use this mic. Yeah, so this is sort of a brief overview of things. So I think in the previous few sessions you have already studied about foundation models, right? And you have also studied about transformer architecture, right? So how many of you remember the transformer architecture? Can you raise your hands? Okay, that's good. So yeah, a lot of you remember. So I'm going to not go into too much details of the transformer architecture, but rather do a sort of a quick recap of transformers. Because this is required to understand the things which I'm going to talk about later, which is the large language models. So I'm going to start with the task of language modeling, which will be followed by like what exactly are large language models and different techniques behind large language models, and how do you build a large language model basically from scratch, right? And in the later part of the talk, I'm going to focus. See, large language models is a very broad area. So, and I'm asked to cover this in like 2 hours or maybe 2.5 hours. And this is like a very, very difficult task because if you, just to give you an idea, in the coming semester, I'm offering a course which is on LLMs, and it's like a 6-month course, right? So I have to compress the entire thing into, let's say, 2 hours. So that's a bit challenging task. So I'm going to not go into too much details of many of the things, but I'm going to talk at a very high level. And one particular thing which I want to talk about is something called parameter efficient fine tuning, or PEFT, because this is one of the prominent techniques that will allow you to use LLMs more efficiently for a specific domain or for some new task for which the LLM, the original LLM or the pre-trained LLM may not be performing so well, right? And this is sort of more on the practical side, so I'm going to talk about that, and we're going to go into details of that. So let me start with transformer architectures. So all the magic that you see that is happening with LLMs, the main thing that is driving all this is transformers, right? So let me start just to motivate the transformer. Let me start with a simple guessing game, right? So you have this sentence: he went to the bank. So when I see this sentence and I look at the word bank, the word bank is sort of very ambiguous for me, right? Because it could be a financial institution or it could be a river bank, right? As you can see on in the two images. It's not clear to me which one of it is, right? So now I continue the sentence further, and I come across this, like, he went to the bank and saw a lot of people. Still the word bank is ambiguous because in both the cases I can see people, right? I mean, in financial institution like bank, there are people, right? And here also you can see people enjoying the riverbank, right? So, but if I continue the sentence further, then I see he saw a lot of people with a check in hand. That completely disambiguates the sentence. The word check, which you see here, gives you complete idea that what word the bank is about, right? I mean, you cannot expect a check to be at the river bank, right? That's very unusual. I mean, until unless you are up to something. Usually the check would be at a river, at the financial institution, right? So one thing to notice here is that to understand the meaning of a word, you actually need to check for the words in the neighborhood. You need to look for the context. And that's what actually is the magic behind the LLMs and the transformers, right? So they try to learn the meaning of a word or meaning of each of the word in the sentence or in any some piece of text by understanding the meaning or by looking at the words in its vicinity or in the neighborhood, right? So that's where the self-attention comes into picture. So I guess all of you would have studied self-attention, right? Like, so how many of you don't know self-attention? Okay, that's good. So everyone knows self-attention. So the intuition, I mean, I'm not going into too much details or the math of it, but the intuition is that you can learn a good representation of a word by focusing on the specific parts of the context. So for example, in our example, in this sentence, he went to the bank. So the word bank, the representation for the word bank should actually be focusing on the representation or on the word check. Right, so you try to, so in fact, when you were looking at this sentence, when you came across the word bank, then, and when I completed the sentence, you started focusing on the word check. Right, I mean, that's, you might have done it implicitly, you may not have realized it, but you would have definitely focused on the word check and you might have just ignored the other words, right? So that's what self-attention also does. It focuses, it puts some sort of weight on a particular word or each of the words in the sentence to learn some sort of a weighted combination of all the words to get a representation. So just to motivate it further, suppose I am a word and I want to, I'm in some sort of identity crisis. I want to disambiguate myself. I want to have an identity. So what would be a way to do that? So I start asking people around me, which is the other words in my vicinity. So I'll go to a word and I'll ask, are you similar to me, or what do you tell about me? So assuming that I am some, so let's frame this problem in terms of like a database. So in databases, I mean, I assume everyone knows databases, right? Like you have a key in a database, and the key is for each of the entry in the database, right? And then someone puts a query. So in this case, it would be a word. I'm going to ask each of the words. I'm basically going to ping each of the key and find out how similar is that key to the query which I'm posing. So the keys which are similar to me are going to likely give more information about me. So that key and query combination will help me to get a sort of a sense of what I'm about, right? So that's what also happens in transformer models. So what you do is, so this is sort of roughly the steps that go on. Maybe can we switch off this light? It's too bright for me, I cannot see. Yeah, so we have, like, for every word, to begin with, we have these so you have, let's say, n words, and each of the words has a embedding, word embedding, right? Like, I mean, in NLP, as you might have already seen, that you need these word embeddings which will capture the properties of the word, right? You start with these embeddings, but then for every word, you also create three vectors: key vector, query vector, and the value vector. And these you get from the embeddings itself by some sort of transformation of the embedding vector via this weight matrix, like WK, Q, and WV, right? And then, as I said in my analogy, I am a key and I'm going to ask, I'm a query and I'm going to ask each of the keys, right? So that's what this operation does. It tries to find the similarity between the key and the query. So let's say I'm particularly interested in some particular word I, right? So I'll get the query for that word I, and I'll start asking all the keys, which is for all the other words, including myself, right? So you can see J is from 1 to N, right? The N words, right? Now, this gives me some sort of similarity score, and then I do some sort of normalization I'm skipping the details here, so that the gradients don't sort of blow up later on. So you normalize the score using softmax, right? And then this softmax is essentially nothing but a probability distribution. So now, for every word, I get a probability about what other words should I focus on, right? So in our example, the word check might be having very, very high probability, let's say 0.8, right? And other words might be having very, very less probability. So now, given this probability score, SI, right, we then weigh each of the value of all the words, which is like an entry in your database, and take the weighted sum. So that gives you the representation for that particular word, the Z. zi. Right, so this way you can do it for all the words, and you get a representation z1 to zn, and this helps you to understand the or get the meaning or the representation of the word. So once you are done with this, and and this is more in sort of a matrix notation. I mean, just for implementation perspective, what you do actually is not multiply individual query vector and key vector and weigh the value vector. What you do is in terms of a matrix. You stack all the queries and keys and everything together, and because at the end of the day you would be putting this into a GPU, and to make it efficient, you have to do it in via some sort of matrix operation. So now, that's the self. So this is what the self attention is. I mean, this whole operation, like you do some sort of matrix multiplication and then softmax and then again a multiplication. So, and in fact, what you also do is, I mean, what I did was just one operation of key and query multiplication and weighing of the values. So that gives me one perspective of the word. But a word is multifaceted, right? So it can have many different aspects to it. I mean, just like any other thing, it has multiple different aspects. But a single key, query, and value may not capture all those aspects. So what you need to do is you want to capture all the possible aspects that are there. So that for that, you create different key, query, value vectors for each of the word. And so each of these is called one head, one self-attention head. And what you can do is you can have multiple self-attention heads, right? Like head 1 to head h, and you can concatenate and then basically multiply by do some sort of linear transformation there, and get the final multi-head self-attention. Right? So this multi-head self-attention is basically what goes as input to the next step. Right, and this gives you the transform architecture, and I assume that you have seen the transform architecture in your previous lectures, right? Like when you might have covered the foundation model, right? So here you can see that you have this multi-head attention. Just to recap there, I'm not going into too much details here. So you have the multi-head attention, and then you would have some sort of a residual connection, which is passing the information from the things that were before multi-head attention, and then does some sort of layer normalization. And then there is some sort of a multi-layer perceptron or feed-forward neural network. And then again, some sort of normalization happens, and then you get these embeddings for each and every word that was there in the input sentence. So this, one thing to note here is, the dimension of this embedding will be same as the dimension as it was in the original input side, as it was at the input side. And this is made possible because we are multiplying by different weight matrices at different stages, as you saw, right? So that ensures that the dimension remains same. And the number of these embeddings will be same as the number of inputs. So this is the encoder architecture. So you encode something, and then you can have something called a decoder. So like just to give an example, like when you are doing machine translation, you're going from, let's say English, let's say you want to translate from English to Nepali. So then what you would do is you will have the English sentence going as input to the encoder, and encoder will capture all the properties of that sentence and summarize it in form of these vectors that you see. And then since you want to do the translation, what you will do is you will have a decoder. So in decoder, what you are doing is, the architecture is same except one difference which happens. Instead of in fact actually there are two differences. One is, instead of just single multi-head attention, you have a cross attention. So cross attention, what it does is, it is having attention over the things it has seen so far, plus attention over the encoder output as well. Right? So that's why the term cross, right? So it is trying to attend to what it has seen or what it has generated so far, plus what was there at the input side, like the English sentence, which obviously makes sense, right? Like since you want to do the translation, you will have to capture the representation of the input as well, right? And the other thing is, in the encoder self-attention, you are multiplying every word with every other word, right? I mean, to get the similarities. But in the decoder, this may not be possible, right? So just imagine like you are generating word. Okay, by the way, these are called as autoregressive model, right? So I guess you have heard the term autoregressive, right? Like it generates one word at a time, right? So now, when you're doing that at inference, you may not know the future words, right? I only know the past, I cannot obviously know the future. So in that case, the attention has to be modified. It can only focus on the words which it had seen in the past. So the attention, what you do is, you have those query key value matrices, but you mask out the values which are coming in the future. So you sort of maybe like, let's say, zero them out, right? So that they don't affect the attention calculation, because at the inference time, when you deploy the model, you will only have access to what it has generated so far, right? So that's also called as causal attention. And we will see this a little later when we go into details of these LLMs, right? So any questions so far? Like, I mean, feel free to ask question in between. I mean, if you have any question. All right. So yeah, I guess everyone is an expert at the transformers now, because you have been going through these for a couple of days now, right? So now, given this background, let's go dive into large language models, right? So you can see there are three words in this phrase, large language models, right? So let's tease apart these things, right? So let's first start with something called language models. So what's a language model? So the language modeling task is kind of very simple, right? And it goes like way back to like almost like 90 in the 90s, or maybe even before that. There were these language models which were used for automatic speech recognition, right? Speech to text kind of things. So the task is very simple. Like, task is, you're given a sequence of words, right? And you want to predict the next word or a token that should come, right? Let's say you have W1 to WK. You want to predict what should come at K plus 1th position. So that's the task of language modeling, right? So as you can see, this is sort of a generative process, because what you're trying to do is model a joint distribution over the entire sequence, W1 to Wn, right? And in fact, if you sort of apply the chain rule over this, what you're doing is, you can factorize this probability into this product of these terms. So the probability of word at ith position is conditioned on all the previous words that were there before, right? And obviously I varies from 1 to n, right? And you have to sort of define some start symbol and all those things just to keep mathematically consistent, right? So that's the task of language modeling. I mean, that's it. I mean, nothing more fancy. And we'll see later that this simple task is actually creating a lot of magic in large language models. And it is really perplexing and very surprising for everyone how can a simple task like this can help models to reason for something really complex, like some sort of like for example, proving a mathematical theorem or coming up with meaning of life, right? I mean, I'm sure everyone has tried this prompt, what is the meaning of life, on ChatGPT, right? And you have all got really interesting answers there, right? Other than 42, right? So as I said, language models have been popular since very, very long time. And over decades, different types of language models have been proposed, starting with statistical language model, or SLMs. So these were some of the initial language models which were proposed, let's say, in 80s or in early 90s, right? And these are, as we'll see, are based on the pure statistical techniques. And then, around 2000, something really interesting happened, and neural language models were proposed. So this was the first time that language modeling task was modeled using a neural network. So at that time, this was around like 2002 or 2003, a very famous paper from Bengio. It came out, and at that time, people still were not convinced that these could do anything. And so that paper came out, and it remained silent for almost like next 10 years or maybe 12 years. and nothing happened. It was all like dead silence. Many people didn't believe it, but there were some few crazy people who believed in it and kept working on it, right? And then around 2017 or 2016 maybe came the PLMs, which completely shattered everything that was there in NLP before. And then the final blow came from large language models. And this moment was around like maybe 2022 when ChatGPT became so popular. I mean, things were going on before that, but actually it came into limelight, right? And it became like, I mean, almost everyone knew about ChatGPT. Before that, no one actually really cared about language models, because before that, people used to think it's just more of an academic pursuit. It may not pay out in the long run. It's just, I mean, just for, showing it can work, but people didn't really believe in it. So maybe let me quickly go through some of these stages, because this will also help you to understand like the perspective about language modeling. So starting with statistical language models, these are also called as classical language models. So the task, as I said earlier, is predict the next word given the previous words or the tokens, right? And these previous words or the tokens are called as context. It's called as context, right? So these were modeled using something called n-grams. And the idea is very simple. If you remember, we had this probability distribution. The joint probability distribution was factorized using the chain rule, right? Where a word at position I depends on all the words that occurred before that. So this is a fairly complex distribution to model, and it obviously requires a lot of data to learn, right? So what was done was a simple assumption was made, which is called the Markov assumption, or in particular n-Markov assumption, which means when you're predicting the probability at word position I, it only depends on previous n-1 words. Rest of the history you can ignore. So that's the Markov assumption. Right, so all the n-gram models that came were based on this Markov assumption, where n could vary. I mean, some people tried unigram, which is just every word is independent, does not depend on anything before. It could be bigram, where it depends on the previous word, trigram, and so on and so forth, right? So that sort of simplified our probability distribution and helps to learn it in a more efficient way, because now you only have to learn this much smaller distribution. And obviously, as you can see, this is an approximation. It's not exact, right? So now, how do you learn these probabilities? Kind of very simple. You basically have a huge corpus of millions of words, and then you count how often a particular pattern occurs, right? Let's say you're modeling bigram. You count how often, let's say W1 is followed by W0, for example, or W2 is followed by W1. You count those, and using those frequencies, you can calculate these probability, right? Like it will be just count of those words occurring together divided by the count of the first word occurring. Right? So simple standard probability calculation. But do you see any problem with this thing? What's the problem with this approach? Can anyone guess? So tell me what happens. Suppose I have a huge corpus of, let's say, 100k words, right? Now I develop this language model, I deploy it basically. Now my language obviously doesn't have just 100k words, right? There would be a lot of new words, or there might be there are certain patterns of words which may not be there in 100k. What do I do when I come across a new word? What would be the probability in that case? So what's going to be the probability in that case? Zero, right? Because you have never seen that word during training. So that means there is a problem here. That means in order to learn a good probability distribution, you need huge number of samples, huge amount of data. And that's what is also called as curse of dimensionality. Right? I mean, these n-gram language model tends to suffer from sparsity issues, because there will always be certain n-grams which will never be there in your training corpus, and as n increases, this will become more and more frequent, right? Because that particular sequence of, let's say, when you have bigram, compare this with, let's say, 4-gram. The chances of those 4 words occurring together will be lesser compared to those two words occurring together, right? So this leads to this curse of dimensionality, and this was a huge problem actually back then. Like and people came up with different sort of techniques, like smoothing techniques where, or maybe back-off techniques where what they do is they use some sort of combination of these n-gram models. So they can combine unigram model with bigram model, with trigram model, and so on and so forth. And other smoothing techniques they were proposed. But those were, I mean, still they were not perfect, right? I mean, they still did not capture a lot of things. And the other problem which you don't realize is that these are modeling sort of discrete patterns here, right? This probability distribution is discrete, it's not continuous. So that means you are trying to model these words, or maybe the frequency of these words, but you are actually not capturing the meaning of these words, right? The meaning of the words is not just those particular combination of the frequencies, right? It goes beyond that, right? So that is missing. And that's where neural language models came into being, to overcome these two limitations. Right? So the idea here was that you represent every word using a word embedding, which is basically a low dimensional compact representation. So everyone knows word embedding, right? Is there anyone who doesn't know what is word embedding? Yeah, so word embedding are basically sort of a vector which will capture the semantic and semantic properties of the word. And the good thing about these is that you learn these automatically from the data itself. You don't have to design this vector. So it's essentially like a feature vector for every word, right? And this is learned using a neural network from the data itself, right? So this was the model which was proposed like in 2002 from Bengio and his group, right? It was a very simple model. What they did was they took every word. Let's say you have these sequence of words, and for every word, using a lookup table, you get a word embedding. And you just simply concatenate those and apply some sort of nonlinear transformation like you do in a standard neural network, and then do the prediction using a softmax. This was the simple, like a very simple feed-forward neural network based neural language model. So what happens is that since you have the data with you, so you can train this model because you know the next word, what should it be, right? Using some sort of likelihood estimate, you can calculate a loss, and this can be used to backpropagate and learn the parameters, including the entries of the lookup table or the embeddings, right? So that's how you learn the embeddings directly from the data itself, right? So, and I mean, this was a feed-forward neural network, but later on, a lot of other approaches like using recurrent neural networks and CNNs and all those things were also proposed. So the good thing about this is that this helps to overcome the curse of dimensionality. And why is that the case? Because now you are learning the embedding for the word based on the word, how that word is occurring in the context of the others. So now, during testing, if you come across a word which was never seen during training, but the words which were in its neighborhood were there, then you will get some sort of meaning of that word from the context in which the word is occurring, right? And this also happens with you, right? Like when you are reading some, let's say some book, and you come across some new word, completely new word which you have never seen. You are still able to get some sort of meaning of that word because you know the context around that word, right? So same thing this neural language model is also doing. So that helps to overcome the curse of dimensionality. And the good thing is that now we are also learning the semantics of the word. This is now a sort of more of a continuous distribution rather than a discrete distribution that we had earlier, right? And so back then, so these embeddings were trained for every task. So they were task specific. And this point will become relevant later on when we talk about embeddings which are sort of more universal, right? So these could only be used for some specific task. These could not generalize across different NLP tasks, right? So obviously these models also, I mean, had some limitation. Like, I mean, they are not generic enough. That's one thing. And also, I mean, they were trained still at a very relatively small scale, right? I mean, the corpus might be just like few hundred words, or maybe at the most few billion words, right? So I mean, the magic didn't happen, right? Because for magic to happen, you needed something really big. And that's what people kept experimenting over years, right? Excluding a lot of efforts, use them for different tasks. But then the meaning of the word changes based on the context. So, and that's what PLM were trying to do, trying to learn contextualized word representation. Which means that instead of now embedding, you store a model now. You pass your sentence or the context through the model and then get a new representation. And every time the context changes, the representation also changes. Right? So now the focus changes from pre-trained embeddings to sort of a pre-trained model. Right? So that's one thing. And then the other thing was, what happened when these were trained at a scale was that they became some sort of a general purpose language learners. Right? You could train, so what you do is typically, like, this is like a bird architecture. You train these using, let's say, this mass language modeling objective, right? And once you have learned the model and the weights of the model, you can adapt those or fine tune the model for different downstream tasks. So for example, you can do something called squad, which is like a question answering sort of a task, and then named entity recognition, natural language inference, and different tasks. So now you can do fine tuning of these models. You don't have to train them from scratch for every different task. So now you can see the shift in focus. Now they are sort of trying to become task independent. Earlier in neural language model, they were task dependent. So now a little bit of task independence comes into picture. And then, okay, so one more thing to note here is that, there were different types of pre-trained language models were proposed. Like one was like encoder only, where if you remember the transform architecture, you only use an encoder along with the mass language modeling objective. And then you learn the representation and obviously the parameters of the model. So that's one. But then they were also decoder only model, where you ignore the encoder altogether and you use only a decoder. So in decoder, if you remember, now you don't have the full self-attention, but you had a causal self-attention, where you only focus on the previous words, not on the future words. Because now in decoder only model, what is happening is, the objective is to predict the next upcoming word. Right? So that means you are going auto-regressively, you are generating one word at a time, right? And when you want to, let's say, generate a word at kth position, your self-attention is only focusing on all the words that occurred before, from 1 to k minus 1. Right? So this is the causal self-attention which happens. So these decoder-only models, started with GPT-1 and then GPT-2 and all the other, like GPT-4 till GPT-4. All these models and in fact most of the LLMs nowadays are actually decoder only. Right? Again, here these were pre-trained and then they can be used for like different tasks, as you can see here. Right? So that was the pre-trained language models, and you can also have some sort of combination of encoder and decoder. So for example, there was this model called T5 which was proposed. So one interesting thing which was done here was that earlier you were giving, let's say, some input and you were doing some sort of prediction or maybe some sort of generation. But here what you do is you train your model has two components. One is the encoder and a decoder, as you saw in the transform architecture. What you do is you frame your task in terms of a natural language. So suppose I want to do the translation, I will write, like here you can see, translate, I will give this instruction in natural language, translate English to German, and then give the sentence. So earlier you were not giving any instruction in natural language. Now you are giving so this is some sort of a prompt, right? If you realize, like in GPT, I am sure everyone has done prompting, right? So this is some sort of a prompt that you are giving. But you can also do other things, like you can have some sort of this COLA sentence. So COLA is some sort of test for changing the linguistic coherence of the model, basically, right? So here you want to check whether this sentence, the course is jumping well, is grammatically correct or not, right? Similarly, you can have like summarize. You give an instruction like you want to summarize something, right? and you give the sentence. So and so forth. So in encoder decoder model, one interesting thing which happened was now you could give some sort of natural language prompts, and the model was able to do the task. Right? Earlier, the concept of prompting was not existing. Now the prompting came into being. Right? And then finally, these pre-trained language models were doing good, but still they were not up to the mark, right? I mean, if you, let's say, had a chatbot based on pre-trained language model, I mean, it will start, let's say it will type starting few sentences, and after that it starts typing either the same word again and again, or maybe some sort of gibberish, right? I don't know if anyone of you has experimented with GPT-2, right? I mean, like GPT-2 was a much smaller scale model, right? It will, if you give a prompt, it will start generating something, but after a while, it will start losing coherence of the thing it is generating, right? So what really needed was something really big, even bigger now, right? So that's where the large language models came into being. Now the scale is completely different, right? So large, like the pre-trained language models were of the order, let's say 1.5 billion parameters, like for GPT-2. Now, let's say GPT-3 was 175 billion parameters. So that's a huge increase in number of parameters and the size of the model. That's one thing, and also the amount of data that is used to train these models is also huge. Trillions of tokens are used to train these models, right? So that's where the large language models come into picture, right? So in fact, these large language models have billions of parameters, like typically greater than 10 billion. I mean, see, the definition of large language model itself is little not clear. I mean, some people even say that, let's say, a model of size 2 billion or 3 billion is also a large language model, right? Like, I mean, you might have seen some models from, like, let's say, Microsoft, like Phi, right? Which is like 3 billion parameter model, and still called a large language model. So this is sort of a little contentious definition, but usually, I mean, I consider a large language model which has order of, let's say, 5 billion or more, or maybe 10 billion sort of parameters, right? And, oops, what happened? Yeah, and so these large language models are based on the standard transform architecture that we saw in the beginning, right? And nothing new actually is there. The main thing that happens is at the scale, it is done at a scale and trained much more efficiently, and also the amount of compute that goes in training these is huge, right? So now, actually it goes more from research to actually engineering, because training these models is not that easy. These have to be trained on huge amount of clusters, and the model, I mean, the training is also distributed, so a lot of engineering goes into training these models. And I mean, from a perspective of research, I mean, it's just the standard next word prediction task, right? So nothing new from research perspective, but from engineering perspective, a very big shift. And in fact, I mean, not everyone can train these LLMs, right? I mean, you need obviously lot amount of compute, but also you need some sort of knowledge about how to train these models, because these have to be distributed over several clusters. And how do you accumulate the gradients? How do you do the batching and all those things? That kind of knowledge is sort of very specialized, right? But the good thing is that these become sort of a general purpose language learner, right? Like, I don't need to emphasize this more. Like, everyone has used ChatGPT, right? And you can see I mean, it's sometimes looks as good as a human, right? Like, I mean, it's almost, I mean, all these large language models have already sort of broken the Turing test, right? So, and you give them any task, I mean, they are able to more or less solve it, right? I mean, obviously they are still not perfect, but I mean, still very, very impressive. And the other thing that happens is now, earlier the task was like classification and all those things, right? Now everything changes to sort of prompt engineering. So if you want to do any new task, you don't have to train the model from scratch. What you would do is you will write a nice prompt. And if you are successful in writing a prompt, the model can do it. So consider the model like a huge knowledge base, which has knowledge about the entire universe. It's your task to extract that knowledge. So if you ask the right question, the model will answer you. If you ask the wrong question, obviously, you won't get the answer. So there's a lot of things inside the model. Now the focus changes from how creative you are about extracting that information. Right, so for example, like, I mean, you can have different kind of prompts, like you can ask, like, explain the gravity, like, in just 50 words, right? So the model will be able to do that. But then you can also have something really complicated, like you give some scientific article, and then you tell, explain this in just 2 sentences, or maybe summarize in 2 sentences, and still the model is able to do that. So when you're doing this prompt engineering, you need to be very, very specific about what you want. Because if you're not specific, then the model will give something really, I mean, it may hallucinate, or it may give something which you were not expecting, right? And similarly, it can do things like, I mean, it can do question answering, then you can also do some sort of classification with the prompt itself. So if you see the shift here, like earlier machine learning models used to be task specific. You give a task, and if you, let's say, give a new task, you will have to train it from scratch, and you give some, let's say you're doing some classification, you give a sentence, it will give a label. Now everything becomes sort of natural language specific. You give a prompt in natural language, and then it does the job for you. And in fact, you can also do numerical problems with it, right? Like you can tell, I mean, ask for some mathematical problem, like how many digits are there in 2 to the 100, and it can go even further. You can also write a code with it. Right? I mean, this is really, really surprising, right? I mean, the model, during training, you never told the model to, or never taught the model to write code. But since it's trained on almost the entire internet, it has picked up a lot of things, and then it can generate code as well. So what happens in large language models is, which is really surprising from research perspective, and is a big curiosity for everyone, is that some sort of emergent abilities come into the model, right? Like, I mean, the model is trained on just simple next word prediction on the entire internet, on huge amount of compute, which might require billions of dollars, and some magic happens and it comes to life, right? I mean, this was never expected. So this is what is called as emergent abilities which come into the model. It is able to solve some complex tasks for which it was never trained, right? So let's look at some of these emergent abilities that occur in LLMs once they are trained at a scale. So one of them is something called in-context learning, or ICL for short. So in context learning, the idea is that, suppose you want to do a task, let's say you want to do translation, right? So you will give one example of that task to the model, and then give the question or the task, and the model is able to do that. So for example, you will tell, translate English to French, and then you will give an example like sea otter, and then the corresponding French translation, and then you will ask cheese as the prompt, and it is able to answer. And you can go further. You can give, instead of just one example, which is called as one shot, you can give multiple examples or few shot, and magically the model is able to do the task. So this is called as in-context learning. Compare this with standard fine-tuning, where, let's say, I have a model which was never trained for translation. If I want to do the translation task with the model, I will have to fine-tune it on these specific set of English and French sentences, right? And this fine-tuning will require gradient updates, and a lot of compute is going to go there. So this is completely gradient free, right? I mean, in context learning, you're not updating the gradients, there's no backpropagation happening. You are just writing everything in natural language, giving a demonstration or demo of the task that you want to do, and the model is able to do. So this is as good as, like, you tell a person that this is what I want to do, and the person is quite intelligent and they will do the things for you. So this is really, really surprising, and this is one of the emergent abilities that happen in large language models. And no wonder you understand why is it called emergent, right? Because, I mean, it's just like, I mean, it just happens after a scale, and no one knows why. And then the other emergent ability which has been observed is something called instruction following, or instruction tuning. So this is also quite interesting. So what you do is, you will create some sort of an instruction data set, where what you do is, you will tell the goal, let's say you want to do some sort of common sense reasoning, right? So you'll tell, let's say, you will give the instruction along with the corresponding answer, right? And you can have different sorts of instructions in your instruction data set. Like for example, this might be common sense reasoning. You could also have translation instruction, right? And you give all these instructions, and then what you do is you fine tune your model on these instructions, and then during inference you give some new instruction which was never there seen in the instruction data set. And surprisingly, the model actually performs much better before you actually gave the instruction, before you did the instruction tuning. So this is really surprising. I mean, I fail to understand why this happens, because you're giving a set of instructions which have nothing to do with what you want to do, but somehow model somehow learns to do for which it was never trained, right? So this is really surprising. So as I said, I mean, I call these large language models as some sort of black hole, right? And they have sucked in the entire information of the universe, and it's there somewhere. You just know, you should know how to get that information from them, right? So, and it really surprises me for the same, I mean, I have like tried out different prompts, and after certain prompts, after a lot of engineering those prompts, I'm able to do the task perfectly. And that really sort of blows my mind, like, and how does it even happen? So in fact, if you compare this with the previous approaches, right? Like, I mean, you would, as I said, like you would fine tune the model and then do all the tasks, right? Or you would be doing the prompting. But in instruction set, you are just giving the instructions, right? And then the other surprising emergent behavior is something called chain of thoughts. So now consider this example, like you have some, like let's say some maths problem, right? Like let's say Roger has 5 tennis balls, he buys 2 more cans of tennis balls, and each can has 3 tennis balls, and then you ask the question, how many tennis balls does he have now, right? So now you give this demonstration via in-context learning, and then you ask some other question, like cafeteria has 23 apples, if they use 20 and bought 6 more, how many apples do they have? But surprisingly, the model gives a wrong answer. And this has been observed for a lot of mathematical problems. No, so now, someday, out of nowhere, someone said, I will, instead of giving the final answer during my demonstration, I will also explain how that I arrived at that answer. Right, like each of the steps, like you said, like Roger started with 5 balls, 2 cans of 3 tennis balls, and so on and so forth, and that's how I get the answer. So once you give this sort of demonstration in via in-context learning, and then you ask the question, surprisingly and magically yet again, the model starts describing the entire thing step by step and gives the right answer. So it is doing some sort of, I mean, I don't know what's going inside, but it is doing some sort of self-reflection there. And one possible conjecture is that, see, these models have also been trained on a lot of code, programming code. So in programming code, you have these steps to achieve some sort of logical operation. So perhaps this kind of behavior is coming from that sort of thing. But I mean, this is just a conjecture. We don't know why this happens. And in fact, you don't even need to do this thing. What someone tried was something really simple. They said, I won't do all this, I'll just say, let's think step by step. And that's it. And surprisingly, models actually starts thinking step by step. It's really surprises me, sometimes makes me feel that actually it's not a large language model, but some person is sitting behind this model who is actually doing the task for me. Right, so this reminds, I don't know how many of you know about Mechanical Turk, right? I mean, the story of Mechanical Turk. Does anyone know about the Mechanical Turk story? So this is, I mean, this goes long time back in Europe. What happened, I don't know the exact time, but sometime in medieval times, there was a person who developed a machine which could play chess. And it was able to beat every grandmaster in Europe. And the person who built that machine, he said that it is some sort of automata which can do the understanding and has some sort of intelligence and can do the task. But actually what was happening was that machine was in some sort of an enclosure, and beneath that machine there was a human who was doing this. So the same feeling I get with these large language models as well. It's like an army of people who are sitting behind and doing all the tasks for me. So this is another emergent ability. So these are the key emergent abilities which have sort of just come out of nowhere: the in-context learning, instruction following, and chain of thoughts. So just to summarize this part, so you have, like earlier, when you develop the statistical language models, you were task specific. Then these became sort of a feature learner. The neural language model started learning some sort of features. Then you came to sort of task solver, where you can you pre-train a model, and then you can transfer that knowledge by fine-tuning these models. And then finally, with large language models, these become a general purpose language solver, just as good as a human, right? So any questions so far? All right, so now let's go further. So over years, these, I mean, there have been several large language models have been proposed, and hundreds of them actually. So broadly, these can be classified into different families, basically, right? So one is the GPT family, right? So this is from OpenAI, which is no longer open, by the way, right? It used to be open at some point, right? And they were open till, they were open till GPT-2, but after that something happened, I don't know what, and they got closed, right? So, so in this OpenAI family, so GPT-1 and GPT-2 were much smaller models, but GPT-3, it was at a different scale altogether, 175 billion parameters, right? And from this, several other families have come up. Like, for example, like Codex, which comes from GPT-3, this was fine-tuned only on code or programming data, and it is able to do the sort of the programming, it is able to solve the programming problems, and also it can help you in writing better code. So like, I mean, I guess you might have used this on GitHub. There's Copilot, right? I don't know how many of you have used and in fact on Google also you have this sort of Copilot kind of thing. So it is able to write the code. I mean, you just write something in some sort of natural language description of the program that you want to write, and it completely generates the entire program for you, right? The entire template for you. So that is what this Codex does. And then there have been, I mean, recently there was this GPT-4, which is completely at a different scale, and we don't know how many parameters it is, and must be order of magnitude bigger than GPT-3, obviously, right? And then, in fact, they have also come up with vision version of that, which can also process images, not just text, right? And I mean, there have been like other GPT versions, like Web GPT. What it does is, like, it'll try to answer your question as much as possible, but at some point it realizes that it cannot answer the question. Then it will go to the internet, query that query, it will send that query to the internet via search engine and get all the relevant documents, and then summarize those and answer you, right? So it's just like, I mean, like, I mean, still, I am still suspicious there's a human behind. I'm quite surprised how can that happen. So that's the OpenAI family. Then, as I described these, okay, so the other interesting thing was this Instruct GPT. So what happened was that when GPT-3 was developed, right, and before ChatGPT, which is GPT 3.5, model was sort of reached saturation. After a while, it didn't start. It was not giving that good performance. So with Instruct GPT, what they did was some sort of a different. There was a sort of a paradigm shift there. So what they did was something called reinforcement learning from human feedback, RLHF. I'm sure everyone has heard the term RLHF, right? So what they did was, for model to answer questions which would be preferred by humans, they try to align the model with human answers. So what they do is, in this 3 stages, basically 3 steps. In the first step, what they do is, so you sample a prompt, right? And then you give to a human labeler, and they will answer the prompt. Now you can do this for several hundreds of examples, and then this you can be used for fine-tuning your LLM or GPT-3. So this is like a standard supervised setting. You have a question and answer, you have lots of these, and you just fine-tune. Next, what you do is, you give a prompt to the model and you ask it to generate not just one answer but multiple different answers. So for example, you might ask it to generate 4 different answers, like A, B, C, D, right? And then you have a human will rank these answers in order of the relevance. Let's say you might say that the D answer is most relevant compared to C, B, C, A or B, right? So you get this sort of ranking over these answers. Now, you can use this to actually train some sort of a reward model. So this reward model, what it does, it will take some sort of a query and the answers and assign some sort of a score, some sort of relevant score for the answer given the query. Now with this reward model, what you can do is you can apply some sort of reinforcement learning over the LLM itself. So now consider, how many of you know about reinforcement learning? Okay, some of you know, okay. Yeah, obviously I cannot go into details of reinforcement learning, but what is happening is that you have a, let's say a prompt. Now your LLM becomes some sort of a policy, which will be, so your prompt is some sort of state and your LLM is some sort of a policy, and it will generate the action or the next token given the prompt. Right, so it is taking these sequence of actions or sequence of tokens that gives you a trajectory, and this can, and along with the reward model, you can give some reward to the LLM and update the parameters. So this is, I'm not going into details, but this is like a standard reinforcement learning kind of setup, and this is done using some sort of a optimization technique called PPO. Proximal algorithm. So yeah, I'll skip these details, but the main idea is that you're now aligning the answers of the model with the human answers. And this is really important because what happens is that model is capable of generating some toxic content or harmful content, right? So you might have seen, like in the beginning when GPT model was launched, people were asking all sorts of questions like how to make a bomb, right? Right, so it will give you the entire instructions, but obviously you don't want your model to do that, right? Otherwise, it's a bad thing. And also, in fact, people were also generating a lot of like toxic content, right? Like some let's say you might want to say something bad about someone or something. All those things you could generate. Now, obviously, you don't want your model to do that. So you want the model to align to human values, right? Which is like you want the model to be non-harmful, obviously. And then you also want model to be truthful and not generate any toxic content, right? Then you, this was with so this was with GPT 3.5. Our LHF became the part of the LLM training setup, and then came GPT-4, for whose details are not known. How much data it was used and how much compute was used, no one knows, but it's a big number for sure, and billions of dollars. And then in opposition to something which is closed but called open, came the Llama family. So these are completely open weight models, which is really good for the community, because now you can use these Llama models and fine tune them, or take the weights and adapt them and do all sorts of things to come up lots of different kind of models. So lots of different versions of Llama have come up, Code Llama and Vicuna, which is Alpaca, and all these are like, some of them are even multimodal. So this actually is really good for the community, because now you know how to sort of adapt these models for your task, and also you know what those weights are, right? So this is, I'm sort of a big supporter of open source, and this is really a big step. And in fact, the new versions of Llama, they are as good as, many times as good as ChatGPT or GPT-4, right? So, and also from the perspective of, transparency, right? And what sort of content that goes in these models, this is a really important step, right? The community can progress only if models are open. Otherwise, you sort of hit a bottleneck, because you don't know what's going behind those, behind the LLM or some chat GPT, right? And similarly, Google also obviously joined the race, right? I mean, it's sort of a LLM race instead of an arms race now. And Google has come up with lots of different models, like starting with Palm and then Gemini and all those, right? So I'm going to not going into details of those. But I mean, see, conceptually, all of them are doing the same thing, nothing new. Huge amount of compute, huge amount of data, and huge amount of engineering. And in fact, the family has been growing. I mean, there's no end to it. Every now and then, a new model comes up. And I don't know if you know, recently there was one model called DeepSeek. I don't know how many of you know it. So that actually came from China, and they made everything open, including the code and the data and everything. Right? So that's a really big step. And this, as I said, like the models have been growing, and I mean, this is just like a small snapshot of it. I mean, you need lots of pages to actually fill this thing. So yeah, maybe is there a time? Is it a time for break now, or? Okay, we'll just take 5-minute break and then we'll continue. Like these emergent properties that are happening in LLMs, right? I mean, there is no clear-cut reason why they are happening, but there are certain key techniques which are sort of behind the success of all these large language models. So I'm going to tell sort of very briefly about some of these key techniques which have led to all the success behind LLMs, right? So starting with one is scaling, right? As I said, like you had PLMs which were some order of some billion parameters, right? Like GPT-2 was 1.5 billion or around 2 billion, and then GPT-3 was 175 billion. So the scale was completely different. So that scaling is actually playing a really, really important role here, and is possibly one of the reasons that all these emergent abilities come into being. And in fact, people have come up with something called scaling laws. So the idea here is that it tries to model some sort of relationship between the model performance, the size of the model, the size of the data set, and the amount of compute. And the model performance is in terms of the loss, basically. I mean, these models are trained using next word prediction, right? So there is a cross entropy loss which is involved. So this actually scaling law helps you to sort of get an idea about, for a given amount of data and compute and the number of parameters in the model, what sort of loss can you expect? Right? In fact, there are two types of scaling laws which have been proposed. So the first one is called something called KM scaling law. So what it does is, it gives a power law relationship between cross entropy loss, size of the model, and the data set size and the amount of compute. So you can see like the cross entropy loss for, let's say, for a given size of the model, which is let's say the number of parameters, for example, the loss is inversely proportional to the number of parameters. That means as the model size grows, the number of parameters increases, the loss will go down. And obviously you want the loss to be as small as possible. Same relationship holds with the size of the data set and the amount of compute as well. Right? So that means these laws are clearly telling you should go bigger and fatter. Right? So you need a lot of data, you need a lot of compute, and you need a huge amount of money also. Right? And so this is the KM scaling law. And the other one is called chinchilla laws. This is based after the chinchilla model which was introduced by DeepMind, Google DeepMind. Right? So the law is kind of similar to the KM scaling law. The formulation is slightly different, but conceptually the relationship is still the same. Right? So here you have the cross entropy loss is a function of inversely related to the size of the data set and the number of parameters. Right? And the constants are slightly different. So by the way, these scaling laws have been determined empirically by experimenting with models of different sizes and different data sets, right? So you basically plot the cross entropy loss for different model size and different size of the data set and different amount of compute, and you get these curves, and from these curves you actually get these scaling laws. But the good thing about these scaling laws is that it gives you some idea about, like, okay, for this particular model performance, how much amount of data should I have, or how much amount of compute should I have, or the other way around, let's say I have this much data and I have this much compute, and this is the size of the model, approximately how much loss I'm going to incur. And this will also give you an idea about what kind of performance the model is going to have, basically. And in fact, I mean, Llama models and several other models have used these scaling laws to actually train the model. So they use these scaling laws to decide the how much data do you need. I mean, because you can see there's a trade-off between size of the data set and the size of the model. So in fact, what people have shown is that you may have a smaller data set, but it's of higher quality, and your model might be sort of smaller, but you can still get the same performance, right? So it's not always the case that you might need a huge model. You can still do with a smaller model, but you need much more high quality data set. Right? And so as I said, like the scaling laws helps you to do some predictable scaling. You know, I mean, what's the relationship between data and thing, and same thing translates to the task level predictability also, because you know the loss will give you an idea about the task performance as well, right? I mean, cross entropy loss, and the task performance is proportional to the cross entropy loss. Lower the loss, the better your performance is going to be. So this is the first technique that has been reason behind the success. The other one is about training, right? So the models, as I said, I mean, from scientific perspective, there's nothing new here. It's the same transform architecture, same next word prediction loss. But what is happening here is you're doing at a scale. So that means that these models have to be trained in a very special manner. You cannot just put it on your laptop and train them, right? You need half of the world's compute to train model like GPT-4, right? So that means a lot of engineering goes into this. And in fact, people have come up with specialized libraries like Deep Speed and Megatron, which actually help you in distributed training of these large language models. Right? So it has become more of an engineering endeavor rather than a scientific endeavor. And then the other is these models, as I showed, are able to do things just with prompting, right? I mean, you give some sort of natural language description of a task, and then it is able to answer. But the trick is that you should be able to describe your problem or the thing that you want to solve in as precisely as possible in that natural language prompt, right? So you, as I said, like these models are like black holes. You should know how to get the information out of these black holes, right? And then the other is technique, which is the alignment, which the RLHF, which I was telling you. So before ChatGPT 3.5, right, or till GPT-3, the models had some decent performance, but still it was not as good as a human, right? But with alignment tuning or the RLHF and other techniques which are there, the model suddenly started showing really, really good performance. So this is really, really important for training really good models. And the other thing which has happened is like, okay, these are LLMs are really good, but still, I mean, they are not perfect, right? So suppose I give some task which might, let's say, involve some sort of calculation. As you might have seen, sometimes it sort of gives a wrong answer, right? Like you might give some sort of complex calculation, it might give a wrong answer. So in that case, what these models can do is, you can connect these models to some standard tools. Like let's say you can connect this LLM via an API to a calculator, right? And what we'll do is, you give a, let's say, give some sort of calculation. It will query the calculator via the API for the calculation, get the answer from the calculator, and return it to you. So essentially, these LLMs can manipulate tools, and this is what actually gives. I'm sure you would have heard about something called agentic frameworks, right? LLM agents. So this is where, I mean, LLMs can actually do the task which is beyond their capability as well. In fact, I mean, you might have seen recently, like Cloud or Anthropic actually came up with a LLM which can completely control your entire operating system, right? It has completely integrated into your operating system, and it can do a lot of things that a standard LLM could not do, because it can, via API, communicate with these different tools and do the task and then return the answer to you. Right? So that's another key technique that has helped the LLMs to make much more progress. So now I'm going to sort of go very briefly into how to build an LLM. Right? I mean, obviously this is like a huge effort, and I mean, I cannot describe it in just few minutes, right? So it's a huge effort, but I'll just outline the main steps which go into this. So starting from collecting the data and preparing the data, to selecting the architecture, then training the model, then aligning the model, and then finally doing some inference or adaptation of the model. So the first step is to train an LLM or to build an LLM, you need data. And not just some data, but huge amount of data. Ideally the entire internet. Right? So what you do, you will have like, you will crawl the web pages, you'll go to social media, Reddit, forums, get the data from there. Then you will use books, like for example, Pile's dataset. You'll use all the data that is there. And this will go into trillions of tokens. So once you have that data, let's say scraped and extracted from books and everything, you cannot just directly use that data and give it to LLM and train. You will need to clean the data. And in fact, okay, other than this, you can also, if you want your LLM to be multilingual, you can collect multilingual text. You can also collect scientific articles, code from GitHub or Stack Overflow and all those things, right? All sorts of data that is there. Once you have that, you cannot just use that data, because see, internet has a lot of garbage as well, right? Not everything is, I mean, well formed and good on internet. So you'll have to do some sort of filtering of that data. So you need to maintain some sort of quality, because if your model, if your data is not of good quality, the model that is going to come out is also not going to be of good quality. So you need to maintain that good quality data. So for that, what you do is you can remove these low quality data using some heuristics, or you could also develop a simple machine learning classifier which will tell, okay, this document is of not high quality. I want something. I don't want to take this for training. And another important thing that you need to make sure is that, see, on internet there's a lot of duplication which happens. Same article might appear in 10 different websites. And it has been observed that if there's a lot of duplication in your data, the performance of LLM goes down drastically. So you want to make sure that the data is deduplicated, which means you remove you remove the duplicate data. It could be at the sentence level or at the document level. And by removing the duplicate data, you're introducing more variety in the data, right? So which also obviously helps the LLM to generalize. So once you are done with deduplication, the next step is, you want to see, internet has a lot of private information as well, right? And obviously you don't want the model to learn someone's, let's say, social security number or maybe date of birth and all those sensitive information. So what you need to do is you need to redact many of these remove PIIs, which is personally identifiable information. And again, you could use some sort of rule-based approach, or maybe you could develop a machine learning classifier which will remove this PII sort of information. Once you are done with that, you then are ready with data to be fed into the LLM, and now comes the step of tokenizing the data. So for tokenization, there are different schemes which have been proposed. One of them, one is like byte pair encoding, word piece, sentence piece, and all these techniques. I mean, I'm not going into details of these because this can take a lot of time. But the general idea is that, typically when you tokenize, let's say, English text, you will tokenize at the white space, right? You will, let's say you use a white space to break the sentence into words. But obviously that is not perfect, because what can happen is that during inference or during testing, you may come across a word which was never seen during training. So what you do is you divide the word, instead of doing the tokenization or breaking the sentence into words, you break them at a sub-word level or sub-token level. And this is what is called as sub-tokenization. And one extreme thing could be you just break them at the character level. Right? And then you learn some sort of way how to combine these characters together to form the word. So during testing, if you come across something new, but it will still have the characters of the language, right? Or the alphabets of the language. You can still learn some good, meaningful representation of that new word based on the characters of the language. So that is one extreme, but you don't go to the character level, but more at this sort of the sub-word level, right? So there are different schemes like byte pair encoding, which basically automatically learns subwords from the frequency of the data itself. And similarly, you have word piece, sentence piece, which use some sort of likelihood, maximum likelihood measure to see which combination of the words will increase the likelihood or decrease the likelihood to come up with this subtokens basically. So once you have decided on the tokenization, then what you also typically do is you will not just restrict the training to one domain itself. If you want the model to generalize, LLM to be good in lots of different domains, you need to mix the sources, or you need to mix the data coming from different sources. And that's where the mixture, that's where you want to do the mixing of this. And then, in fact, what you will also do is, you will be smart about training. What you will do is, you will not just train everything in a single go, but change the data mixture as you progress with training. So for example, in the stage 1, you will start with some data source which is more about general English, right? I mean, you want the model to learn some grammar about English. For example, if you are training English LLM, so you want the model to learn about grammar of the English and how the sentences are formed and all those things. But then as you progress during training, you will start decreasing the proportion of this kind of data and start increasing the proportion of other domains, right? So that your model gets specialized in different domains as well, right? So this is some sort of a data scheduling that needs to be done. And the better your scheduling is, the more generalizable the model is going to be, right? So obviously this is a huge engineering perspective, right? So yeah. And then once you are done with that, once your data is ready, now you need to decide on what sort of architecture that needs to be trained, right? So there are different types of architecture, and we saw example of those, right? Like one was the encoder-decoder architecture that we saw, then causal decoder and prefix decoder, right? So encoder-decoder you already know. Causal decoder, I said, like you only focus on the words in the self-attention. You only focus on the words which were there in the past. You do not see the words in the future. And in prefix decoder, what you do is you do two things. One is you have bidirectional attention over the prompt that is given to the model, and unidirectional attention or the causal attention over the text that is being generated by the model. So in causal decoder, you are doing only unidirectional attention, right? Because you're only focusing on the words that have been generated so far. But in prefix decoder, what you're doing, you have a mix of bidirectional and the causal attention, right? Any questions, Subhan? All right, so once you have done, decided on the architecture, then you need to obviously decide on what sort of modeling objective that you want to do. You could start with language modeling object, standard language modeling objective, or you can have denoising sort of autoencoder. What you do is you corrupt some of the words in the sentence and you want the model to predict those corrupted words. So that's another objective that you could use. Or you can have mixture of language modeling and the denoising autoencoder sort of objective, right? So then once you have decided on the objective, then you start with the training, right? And in training, you obviously need to decide on optimizer. Typically, Adam and AdamW optimizers are used, and they have worked really well for most of the models. And then you also need to decide on the size of the batch, right? And typically what you do is you need to have batch of decent size. Like for example, a batch of 4 million tokens is really standard, right? Which might be like around 2000 examples, right? And in fact, what you can also do is you can change the batch size as the training progresses, right? And then you obviously need to decide on the learning rate, and you can have different schedule for learning rate. So suppose you start with a simple warm-up let's say you increase your learning rate from, let's say, 0.1% to 0.5% of the number of training steps, and then you start going cyclic sort of learning rate, which is like sort of cosine learning rate as you progress in training. Right, and then obviously, see, these models are not that straightforward today, especially that you're doing at a scale, right, and it's distributed. So you need to make sure that they are, the stability is maintained. Otherwise, they can easily collapse, right? So using various learning rates and batch sizes, you need to maintain the stability of the model. And then during training, see, as I said, this is sort of a specialized training, like a distributed training. So you can actually need to distribute the model across GPUs or across servers. There can be different ways of doing it. One is like data parallelism. So what you do is you put the same model across different GPUs, but you divide the data across these GPUs. And then you get different versions of the model, and then you aggregate those. Maybe, for example, by averaging the gradients. Other could be pipeline parallelism, where what you do is you distribute the different layers of the LLM across GPUs. So one layer, or maybe couple of layers, might be in one GPU, couple of layers might be another GPU, and then you train this, and then you aggregate the information, aggregate the gradients. And the other is the tensor parallelism, where what you do is, now you break your, let's say you have these weight matrices. What you can do is you can factorize these weight matrices, right, into smaller matrices, and then do the operation on these smaller matrices, using these smaller matrices, and then combine them together later. So for example, a matrix W can be basically written as A into B, right, and then each of these A and B could be learned separately on different GPUs, right, and then you combine them later, right, because these weight matrices, some of these might be huge, right, so you break them into smaller matrices. So these are like different types of ways of distributing the model across, or distributing the data across different GPUs. And then once you are done with training, then your job is still not done. You still need to align the models with the kind of responses that you're expecting. So that's where RLHF comes into picture, which we saw. You can also do some sort of supervised fine-tuning, where you have human responses, and then you fine-tune the model on those human responses. And then obviously you can also do instruction tuning as well. So these things are really important so this is like the last mile which has to be traveled before actually you have the model ready. Without this, it may not perform that well. And we already saw RLHF, right, just a few minutes ago. And so finally now you're successful and your model is ready. You can use it, but still it's not perfect. During inference, it might happen that you come across some completely new domain for which the model was never, for which the data was never available during training. So now you might want to adapt your model, right? So one simple approach could be you just simply fine-tune your model, but your model is of 200 billion parameters. You cannot fine-tune such a model. I mean, it's going to be very expensive. So for that, people have come up with different techniques like low rank approximation, distillation, quantization of the model. So I'm not going into details of this. We will just see some of these details in the next part of the lecture when I talk about PEFT, or parameter efficient fine tuning. So to conclude this part, see, I mean, as I said, like these models are huge and they are like black holes. We don't know why and how these emergent capabilities arise in LLMs. So this is still an open question and open research problem. How does in-context learning work, basically? No, I will continue because I want to continue one more part, PEFT, maybe an hour or so. So we'll squeeze the lab session. So this is an open research problem. If any, I mean, it's sort of open for people to explore, right? And then see, the other problem is that training these LLMs is very, very difficult, right? Huge amount of compute, huge amount of money is required. So is it possible, and this is not possible in academia for sure, right? And is it possible to come up with more efficient way of training it, or are there more efficient architectures which can be used? I mean, some progress is happening in these, like for example, state space language models have been proposed, but still there's a long way to go for them to have performance similar to these large scale language models. And finally, see, these, I mean, RLHF has been proposed, but still, I mean, LLMs are not completely aligned with human values, right? And, I mean, still you can trick them to generate toxic content. You can jailbreak them to generate toxic content. And in fact, models still tend to suffer from hallucination. And I'm sure many of you have seen that when you ask ChatGPT, it tends to answer something which even doesn't exist, right? So for example, I will give, so I work in like the legal domain, and once I was trying to do some task, legal NLP I work in, I was trying to do some task with legal NLP with ChatGPT. I gave a document, legal document, and then it started its own line of reasoning, and it invented some laws which even didn't exist. And I was completely shocked to see that it was referring to certain section of the Constitution of India, basically. I had given an Indian legal document. And when I actually referred to that section, that section was not even there. So I was really surprised that it invented something on its own and then started line of reasoning using that. So that was really, really surprising. And in fact, I mean, some lawyers, I mean, I will just give you a sort of a funny anecdote there. So some lawyers actually in India were using ChatGPT for drafting their plea, and again there the model hallucinated and it came up with certain statutes which were not there. And when it went to the judge was really shocked to see that, and he took a really, I mean, he actually penalized those lawyers for using ChatGPT for generating the draft of the document, because there was a lot of hallucination which was happening there. So yeah, I mean, you cannot trust ChatGPT completely, and you need to be really careful about using it. Yeah, so to summarize this part, I mean, definitely LLMs, I mean, are a big step towards building artificially intelligent systems, right? And we can see they have been trained at a scale, and they have become sort of a general purpose language learner. And they can be applied to a variety of tasks, I mean, many of them which have never been seen during training, right? But still, I mean, they are still a long way to go. They're still not, I mean, like, I mean, as Jan LeCun also says, I mean, these are not still like perfectly intelligent machines, right? So there's still long way to go, and then suffers from a lot of challenges like hallucinations and and you don't understand what's going inside. I mean, they're still black box, right? So which also means that there are a lot of good research opportunities as well. So next part I'm going to talk about is how do you use these LLM in practice, something called parameter efficient fine tuning, or PEFT. So maybe we can take a break now, right? Or yeah, so we'll take a break, and after the, I think this is a lunch break, right? So after the lunch we'll meet again, and we'll continue with this PEFT thing. This more practical aspect. This will be what you will also be doing the hands-on on, like. So I have developed an assignment. This is in Google Colab, so you can actually train some model and use these PEP techniques to fine-tune that model on some specific task. Shall we get started? Okay, so, all right, so far we have been looking at the LLMs, right? Like I sort of gave a broad level, very broad and high level overview of different techniques in LLM, how to build an LLM, and emergent properties in LLM and all these, right? I didn't go into too much depth because this requires a lot more time. Now I'm going to talk about something more practical. So you have, let's say, a very well-trained LLM model, like a pre-trained model, right? And this model is huge. So one way to use it, you just prompt it, right? But prompting doesn't always work. So it might happen that at some point you come across a domain or a new task on which LLM has never been trained. How do you use this LLM? what can you do? I mean, obviously you cannot fine tune it because it's huge, billions of parameters. So can you do something more efficient? That's what we're going to explore now. And this is what is called as parameter efficient fine tuning, PEFT for short. All right, so is everyone ready? I hear a lot of noises. All right, so okay, so we already know about the transformer architecture, right? We saw this, right? Now let's see how to use pre-trained LLM for new tasks and domains, right? So one way is, we already saw, is what you can do is you can use this LLM. Let's say you have a pre-trained LLM or language model. It has weights frozen. What you can do is you pass your input to the model and you get some sort of output embedding or representation for the input. And then using this representation, you can train a classifier, like a simple machine learning classifier. It could be a simple MLP, multi-layer perceptron, or a logistic regression, or even a SVM, right? And then what you do is, in this, you are only training the weights of the classifier. You are not changing the weights of the LLM, it's frozen. So here, you're using the LLM as a feature extractor. So it takes in an input, extracts features, and then using this using these extracted features, you can do classification, for example. Right? So that's one way of using it. Other way is you do something called partial fine tuning. So what you do is, okay, I will not, so my LLM is large, I will not fine tune the LLM for all the weights of the LLM, but what I will do is I believe that the upper layers of the LLM has more of semantic information which will be useful for my task, like let's say for some prediction. So what I will do is I'll take the let's say upper few layers and fine tune them, right, and keep the lower layers frozen. So what you're doing is you give the training data, pass it through the LLM, and then also you have a classifier on the top, and you get some output here, and then you calculate the loss using this output, and then what you do is you backpropagate. Everyone knows backpropagation, right? So you backpropagate, update the weights of the classifier, and also update the weights of upper few layers, but don't update the weights of the lower layers. So those are frozen, right? So this is sort of partial fine tuning. And then the other method is full fine tuning. What you do is you fine tune the entire LLM, which is all the parameters in the LLM, all the weights in the LLM. You give the input, pass it through the LLM, pass it to the classifier, get some output, calculate the loss, backpropagate all the way through the LLM to the input. Right? So that's the third way. So obviously there is a trade-off here, right? So what sort of trade-off is there? Like which one is will give better results? Which one will give better results? Okay, how many of you say that the third one will give best results? Okay, few. And how many of you believe in second? And so I assume the rest are on the first, right? Yeah, so see, there is a trade-off here. What happens is, if you plot performance versus the training speed, so the feature extraction one, the first one, will obviously be very, very faster because you are just using it for doing inference, getting the features. But performance-wise, it will not give the best performance because you are just extracting the features, right? Whereas the full fine-tuning, you are updating the weights, and these weights are tuned to a specific task. So this will give you the best performance, but obviously it will be much slower because the LLM is large, so you'll have to backpropagate through the entire LLM. So that is going to slow it down, right? So that will take a lot more time, right? So you see the trade-off that is happening here, right? Between how many weights you are updating and how much performance you are getting, right? So now, but in modern day, the number of the size of the LLMs is growing almost like exponentially, right? If you see, the size of LLMs starting from, let's say, before 2020, in just 4 years, it has gone from, let's say, the BERT was like few hundred million parameters to order of, like, it's much more than 175 billion parameters, right? It's order of some trillion parameters. So each dot here is one LLM, and the size of the dot tells how many parameters it has. So you can see, like, I mean, this orange dot which you see here, this is Gemini Pro. It's already such big model, and this, the baseline is here like 125 billion. So you can see it's already much bigger. So assume that I tell you, now we just saw that full fine tuning gives the best performance. Can you do full fine tuning on this huge model? Right? Obviously you will not be able to do it. Right? In fact, if you see, like, the evolution of these LLMs, right? Let's say starting from GPT-1, which has very less, like just 0.1 billion parameters, and then you see the amount of training, the training cost, like petaflop per day. So if you see, as the model size is growing, the number of petaflops per day that is required is growing like crazy, right? Like, I mean, for example, if you see this one, Palm model, which is 540 billion parameters, it's almost like 30,000 petaflop per day. That's huge, right? So, I mean, obviously fine tuning will not work. And in fact, there is an estimate, like, as you can see that this is the number of flops that are being used by the model. It's almost like growing linearly. And in fact, there's a study which says that model size scales almost 2 orders of magnitude quicker than the computational resources. So if you remember, back in days we had Moore's law, which says like the compute doubles, right? That, I mean, does not help at all. Here the model size is growing much faster than the scale at which the compute is growing, right? So that leads to a problem. So now we're going to see, can we do something really better? Can we still get really good performance without doing full fine tuning, right? And without incurring a lot of compute and inference time. But before we do that, so one way of doing it is you just do in-context learning or hard prompting. It's also called hard prompting. So idea is that you don't want to change the parameters of the model. You want to have a gradient-free method, and you basically what you do in you want to guide the model towards a particular task of interest, right? So what you in context learning, what you'll do is you give instruction in natural language via prompt, right? Having some examples or demonstrations, right, of the task, and then you give a unlabeled example, and then it just gives you the answer out of magic, right? And this, I mean, we already saw the example of this earlier. Like, you're giving, let's say you're doing sentiment analysis, you have like delicious food has label 1, food is awful has label 0, terrible dish is 0, and then you give these examples, and then you give a review text and the label, and then it suddenly predicts whether it's a positive label or a negative label, right? So this is in context. We already saw this, right? And this in context learning we also saw is an emergent property, right? And the other advantage with in context learning is it allows mixed batches, which means you can have really different tasks put into a same batch. One task could be about sentiment analysis, another task could be about, let's say, question answering, another task could be about named entity recognition, and all these are very different tasks, but within the same batch that you give for inference, it will still work. So that's the sort of the beauty of it. And we have already seen these ICL examples. Maybe I'll skip this part, right? But in context learning is not the solution. Firstly, I mean, there are downsides to it. One is it's quite computationally expensive because you have to do inference. So for inference, you will have to give, I mean, for giving, let's say you're doing K-short in context learning, right? So for inference, you will have to do K examples for getting output for one sample, right? So this, and plus, you should remember the attention that is being done
is also quadratic in complexity. So that is really computationally expensive operation. So this will not help. Then from memory perspective also, in context learning is very expensive operation, because you will have to store k examples, right? So it will grow linearly in k. Plus, this has to be stored on the disk. The storing cost of the prompts itself on the disk is there. The other problem is that, okay, you are giving these examples, but you should remember the LLM has a finite context length, right? You can give only finite number of tokens or words in the LLM as input. Now, if some of those tokens are already taken by the examples or demonstration, then you have very less left for the task that you're trying to solve, right? So that creates another problem. You can increase the context length, but obviously, it comes at a quadratic complexity, so it doesn't help. And the biggest thing is that, and this all of you know, that prompt engineering doesn't work in the first time for sure, right? Like you have to experiment a lot of prompts till you come to a perfect prompt which will solve your problem. So there's a lot of engineering effort which goes into designing these prompts, right? And also people have observed that these prompts are really sensitive. You change one word in the prompt and it completely changes. You change the order of the examples in the prompt, it changes. You flip the examples, you give one example and you change the label to some other label, and in context learning will fail. So it's really sensitive. I'm sure people who have tried prompting, right? We have seen that I put one full stop and completely different output came out, right? So it's very sensitive, it's not stable. And in general, the performance is not as good as full fine-tuning, right? We saw that full fine-tuning gives really good performance, but we are not getting there. So I hope I have convinced you that in-context learning or prompting will not solve your problem, right? So any questions so far? All right, you have a question? Yeah. Yeah, there is a mic. There was one mic here, right? Mm-hmm. Yeah, you have to switch it off. You have to just.
Does it work?
Yeah.
I was wondering if the techniques for prompt engineering, if they generalize across different models, so if you have a prompt that works very well for one.
No, not really. Not always. Sometimes it might, sometimes it may not. And as I said, these the models, different models have been trained in different ways, and usually on different kinds of data. So the emergent property that is there is also slightly different. So if you use, let's say I develop a prompt from ChatGPT and then I try to use it in Llama, may not always work. There's no guarantee. So now that brings us to PEFT, parameter efficient fine tuning, right? So the motivation is, LLMs are really good language learners, we have seen, but still they may not generalize to every new domain, right? So we need to we need to fine tune the LLMs to a new domain to get good performance. But as you know, I already showed you that size of the models has been increasing like crazy, right? You cannot fine tune the LLM. It's really expensive operation. So what PEF does is, it involves training only a small set of parameters which might be subset of the existing model parameters or a set of newly added parameters, while keeping rest of the model frozen. Right, so you have a very small tiny fraction of parameters which might be updated, or you might add some small tiny fraction of parameters, and only those are going to be updated. And obviously PEFT is specific to a task. You can't fine tune a model with PEFT and then expect it to work well on some completely new task. That doesn't, that kind of emergence has not happened till date, right? So there are emergent capabilities, but still we are living in a sort of we are not completely in a stochastic world, right? Like still, I mean, there is some sense in this world. And over years, I mean, okay, when I say years, maybe I should over months. I would say, I mean, because the field is growing like crazy, crazy fast. So, over researchers have come up with several types of PEP techniques. Here you can see like there's a huge table and like 50 plus papers on PEP. I mean, this is like a very small subset. I mean, there are even much more papers on PEP, right? But if you see closely, all these PEP techniques fall into three categories. One is additive PEP, selective PEP, and reparameterization. So we're going to look into details of these. Starting with additive PEP. So in additive PEP, this is what you do is you introduce small set of parameters, and these parameters into the LLM, and only these parameters are updated, right? And nothing, everything else remains frozen. So what you do is, let's say you are given a new task, you are given certain input. What you'll do is you'll pass it through the, let's say you add these small set of parameters, you randomly initialize them, you pass the input through these, it'll flow, I mean the information will flow from the LLM as well as these trainable parameters, right? And it goes there, and then during backpropagation, the information from the loss is going to backpropagate only through the trainable parameters, because the remaining parameters of the model are frozen, right? So you only update these parameters, rest everything is frozen. And this is called as additive tuning. And the reason is obvious, right? Like you are adding small set of parameters, right? And in fact, there are three main types of additive tuning. One is called adapters, another is called soft prompting, and I mean the combination of the two. So we're going to look into details of adapters and soft prompting in a bit. So any questions on this? Is it clear? All right, so the other one is selective PEFT. So in selective PEFT, what you do is, so you are not adding any new parameters as you are doing in additive. So what you do is select a small subset of parameters and only update those. Right, so for example, you have this fine-tune, you have pre-trained LLM, you pick up small set of parameters within this LLM, and during backpropagation, you only update these. Rest everything is frozen, right? So, and the name is clear, I mean name is obvious. Why is it called selective? Because you are selecting small subset of parameters which are getting updated. So to put it more formally, let's say you have these parameters in the model theta 1 to theta n. Then what you do is you apply a binary mask to each of these parameters. So this mask can be 0 or 1. You apply to each of these parameters, right? And the way you update is, I mean this is the standard gradient update, right? Like if you have seen in gradient descent. So you update the parameter, each of the parameters is updated using the gradient update rule. But the only difference here is that you multiply each gradient by a mask, which can be 1 or 0. So for the parameters which you don't want to update, obviously the mask is going to be 0, right? So mask will be 0, and the parameters which are going to be updated, the mask is going to be 1. Now the question is, I mean, how do you decide this mask? I mean, you have a huge number of parameters. There has to be some automated way of deciding these masks, right? I mean, you cannot do it manually, obviously, right? So there are different techniques which have been proposed. I mean, I'm going to show only some of them. I mean, the list is huge. So one is something called differential pruning. What you do is you apply a binary mask to each of the weights, but this mask is penalized by L0 norm. So you apply, I mean, you're penalizing the mask. So what's an L0 norm? Does anyone know what's L0 norm? Yeah? Dimension? Not really. the total number of non-zero items. Yeah, number of non-zero values in the vector. That's the L0 norm. Right, so you penalize these masks, and obviously, I mean, you put it into as a regularizer in the loss function, and then you do the same thing, backpropagation and all those things. The other technique is called PAFI. So what you do is you prune the weights or prune the things based on the magnitude of the weight. So you select parameters which have smallest magnitude, and you only update them. The parameters which have high magnitude, they are not updated. Another technique is called fish mask or Fisher information mask. So what you do is you again select top k parameters based on Fisher information matrix. So Fisher information matrix is some sort of statistical measure of importance of that random variable, which is in our case the parameter itself. I'm not going into details, you can check out, it's a fairly standard thing. Calculation of Fisher information matrix is fairly standard thing. And then there is fish dip, which is similar to fish mask, except that the mask is dynamically calculated in each epoch, right? In fish mask, you were doing it preemptively before you started training. Here you do it dynamically during training. And then there is something called LT SFT. So idea here is that you select the parameters based on lottery ticket hypothesis. So does anyone know what is lottery ticket hypothesis for neural networks? All right, so see lottery ticket hypothesis suggests that in a huge large network, there exists a small, more efficient subnetwork which will give the same performance as the original large network. It's like winning a lottery ticket within small subnetwork is like a lottery ticket within a huge network, right? So this is, and there is a specific, there is a technique of selecting this subnetwork using, there's an algorithm which helps you to select this subnetwork, and that's what is called as lottery ticket hypothesis algorithm. So I'm not going into details of that, but it's based on some sort of pruning of the weights based on the weights, or maybe some sort of information content in those weights. And then another is called bitfit, where you only fine tune the bias parameters in each of the DNN layers in the transformer, and you don't touch any other things basically. So these are some of the techniques for deciding the mask, but there are several others as well. So any questions on this? All right, so now the third type of PEFT technique is called reparameterization, and this is the most interesting one. So idea here is that what you do is you transform the model architecture from one form to the another, and this form that you have transformed into is easier to sort of train or fine tune, right? So for example, you can construct a low rank parameterization of the weight matrix, and a low rank approximation of the weight matrix essentially. And this low rank approximation is much more efficient to train or fine tune, right? And one of the most popular technique, which we are going to look into details later, is called low rank adaptation, or LoRa, right? And I am sure many of you might have used LoRa for fine tuning your LLM, right? And also in today's lab, we have this LoRa fine tuning as one of the exercise. And the good thing about this is that during inference, what you do is you simply merge the LoRa or these reparameterized weights into the original weights of the model. So from inference perspective, there is no additional overhead because the number of parameters remains same, right? So this is super efficient, and this is, when usually someone talks about PEFT, they are usually referring to LoRa and these kind of techniques, right? So in this lecture, I'm going to focus on, so these were like different PEFT techniques, and in this lecture, I'm going to focus on three main PEFT techniques which are very popular and most often used. One is called soft prompting, one is called adapters, and another one is called LoRa, which I just mentioned. So let's start with soft prompting. Any questions so far? Is there a question there? I'm not able to see though. Okay, no questions. Okay. All right. So in soft prompting, so you saw in context learning, right? We were optimizing the so in context learning or ICL is called hard prompting, because what we are trying to do is via prompt engineering we are trying to optimize the discrete tokens which are given as prompts to the LLM, right? Another way could be, what if instead of giving these discrete tokens, we gave continuous representation or embeddings as input, like for example as a prefix to the task that we want to do, and fine tune these embeddings along with the rest of the parameters of the model. Or maybe just don't fine tune the parameters of the model at all, you just fine tune these embeddings which are given as soft prompts to the model along with the task. And no wonder this is called as soft prompting, right? So this is sort of a lightweight fine-tuning method, because very small number of new parameters are added. Because these small, I mean, you are just giving a new learnable embedding, which is like acting like a prompt, like a natural language prompt as input to the model. And obviously this embedding is much smaller in size than the total number of parameters in the model. Right, so just to put it more formally, like you have this task specific tokens like x1 to xn, nx, right? What you do is you give these soft tokens s1 to sns as input to the model, and then what it does is the model will fine tune or learn the embeddings or update the embeddings of these only and nothing else. So these embeddings or these soft tokens are going to be task specific, and we'll just see how that works, right? Will not correspond to any real words in the dictionary and may not be even interpretable. So see, like in prompting, what you're doing is you're giving let's say I give a prompt, summarize this sentence, and then you give the text that has to be summarized. But in soft prompting, you will just give the text and prepend and apply your soft prompt tokens. Let's say you apply k tokens, soft tokens, before the actual text, and these tokens are obviously going to get mapped into embeddings, right? Because every token gets mapped to embedding in transformer, and these embeddings are actually going to get updated when you're doing the fine tuning, and rest everything remains frozen. So in a way you are learning a virtual tokens, and that's why I say that these tokens that you have learned are not interpretable and may not correspond to actual words in the dictionary. So this is kind of similar to ICL, but with dynamic continuous differentiable prompt, right? And obviously we always love things which are differentiable, right? Because it helps in doing backpropagation and all those things. And as I said, I mean, the fine tuning is forcing the model to automatically learn the right context, right? I mean, see, why does prompting work? Because prompting works in some ways because you are giving the right context. You're creating the ideal situation for model to continue generating the answer, right? So this soft prompting is providing that context, but in an automated way via these differentiable prompts. Right, and the good thing is that you don't have to do any manual prompt engineering, right? I mean, earlier you had to try 10 different or 100 different prompts till you achieve your task or goal. Here, you just have to fine tune to get that place. Right, so let's look at something, one particular type of soft prompting which is called prefix tuning. So what you do in prefix tuning is, you prepend a sequence of continuous task-specific vectors called as prefix to the keys and the values of each layer of the transformer. Right, so in transformer, if you remember, in the architecture there was key and value things, right? So to every key vector and each value vector, you append these virtual tokens which are going to get updated. So for example, let's say you have this transformer architecture and you have different tasks that you want to do. Let's say you want to do a task on table to text, where the task is that you're given a table, let's say in a linearized form, and you want to generate the summary of the table. Summarize the table or describe the table. And then there could be a task like summarization, right? I mean, we have seen this. Then there would be a task, let's say translation. So what you do is, you have pre-trained transformer, you give the tokens as input, let's say you have this table to text task, and you give this linearized table like name, Starbucks, type, coffee shop, and so on and so forth. And you also give a soft prompts. Like here you can see these two things. These are two soft prompts which are given along with the input, and then the model will generate this output. We can see like a summary of the table, Starbucks serves coffee. Similarly, you can have a soft prompt for summarization, you can have soft prompt for translation, and so on and so forth. So you can see that this is really plug and play sort of setting, right? You train a soft prompt for one task and another task, and then you can just plug out that, plug in another. You don't have to change anything in the model at all, right? So this is pretty neat and convenient, right? So what happens is that the actual input so this, as I said, this is attached to the key and the value. So during self-attention, the input tokens attend to the prefix tokens, or as we call it as virtual tokens, and they help in setting these virtual tokens to get the context right, so that it helps to solve the task, right? And during fine tuning, you only prefix tokens are optimized. And you keep, as I said, like you can keep one copy of the model, and task prefixes can be stored in the memory, and you can do sort of plug and play. But the good thing is these task prefix vectors are much smaller, or very less number of parameters compared to the data model, almost like the factor of 1,000, right? So this is super efficient. And as I said, this is very modular. I mean, you can just keep a library of these different task vectors, right, or prefix vectors, and then you can, whenever there is a requirement, you can plug in, you can pull out one of those vectors of interest and then plug in into the model and solve the task. And it also allows like multitask and multi-user batching. So that means what you can do is, within a batch, you can have different prompt vectors or prefix vectors corresponding to different tasks. And you can, in fact, you can also, this allows some sort of personalization now, because you can have prefix vectors specific to a person. Suppose I have a small LLM in my mobile device, and this LLM has to be tuned to my preferences or my way of using the things, basically. So I can fine tune this LLM using these soft prompts, and I keep the copy of this. Another user will have another copy, and so on and so forth. And whenever the need is, you can just use things which are specific to you, and without any data contamination between different users, basically. So, so now the question is, I mean, we are doing this soft prompting or giving these continuous vectors, right? Why can't we directly optimize for discrete prompts itself, right? Why can't we do that? I mean, instead of giving these soft prompts, I can just, why can't I have an optimization where I will select the correct words from, let's say, a vocabulary and give them as prompt? Is that feasible? I mean, just think about, like, let's say I have 10, let's say a prompt of 10 tokens. For every token, I have a dictionary of, I have to select from a dictionary of, let's say, 40,000. So how many possible combinations would be there? So first space can be filled in 40,000 different ways, right? Similarly, second one, so you'll have huge number of combinations, right? 40,000 times, till, I mean, do it 10 times, right? So that is like a computationally very expensive optimization, right? It's very hard to solve. So that's why we can't do hard prompting optimization. That's why you go for soft prompting. Right? And another good thing is that it is task agnostic, because I can do a prediction task but also a generation task as well. I just have to plug in the right prompt, right? I mean, I can mix tasks basically. So as I said, the main intuition here is that you want to drive the LLM to learn a good context, right? So for example, if you want to generate word automobile, then one of the appropriate contexts would be like drive or travel or something of that sort, right? So what happens when you are doing fine tuning is the model is forcing these prefixes to take the form of those context which will help in generating the right token, right? So that's why this whole thing is working. That's how this prefix tuning is working, right? And I mean, you can get the intuition also from prompting itself, right? Like hard prompting itself, when you know when you set in the correct sequence of words, then only model generates the desired output, right? So same thing here is happening, but in an automated way, driven by the data itself and the task, yeah. And same thing can be done at the, I mean, this I was telling at the word level, but the same thing can happen at sentence level when you have paragraphs involved, basically. Right, and yeah, maybe. So the other thing is, as I said, like when you are doing prompting, right? I mean, beforehand, it's not even clear that, I mean, what would be the ideal prompt like? Till you actually start searching through all these prompts, trying out different prompts, right? So it's not, as I said, it's a discrete optimization problem which is really hard to solve. And you just try a few prompts and it works, and sometimes it doesn't work at all, right? Because you have not got to the right sequence of those tokens, right? So that's why we use this sort of soft embeddings which take care of all these problems, basically. So maybe let's look a bit formally like how it's happening. So let's say you have some task of like conditional generation task. Like for example, you want to do some sort of table to text. You have a table which is linearized, and then you want to generate the description of the table. Or maybe you have a summarization task. You are given some document and you want to generate a summary of this. So in these tasks, the input is X, which is the context, and the output is the sequence of tokens, Y. Right, and there are two types of model: auto-regressive language model and the encoder-decoder. We have seen these two models before, right? Like auto-regressive is like sort of decoder-only model, where you generate token by token. Given some prompt, you generate token by token. And encoder-decoder is in the encoder, you are giving the prompt as input to the encoder, and then there's a decoder will generate auto-regressively. So in the autoregressive model, you are basically modeling this distribution of P of phi, y given x, right? Parameterized by this phi parameters, right? So here, if you can see, each of the x input is mapped to an indices, right? Like you can have like different indices for each of the words in the input, and each of the target also has mapped to a certain indices, right? And these then get converted to embeddings and all those things we have seen before. And at each layer, let's say at layer I, you are getting this hidden representation, right? And which are basically concatenated. So H is basically activation of the jth transform layer at time step I, right? And then what you are doing at the final layer, you are actually given all these context X and Y. So Y is the text which has been generated so far. Along with the activation, you get the next activation. And at the final layer, you do the softmax over the HN. Right? So this is like the standard thing we have seen in transformer as well, right? Like you get the activation from each layer, and then at the final layer, you do the softmax to get the next token. And same thing is happening in encoder-decoder model also, except the difference is now you have to pass through the encoder, the text, input text, and you are adding the prefixes or soft tokens at both encoder side as well as the decoder side. In the autoregressive or decoder only, you are adding prefixes only at the decoder because that's the only thing you have basically. So essentially, in fine tuning is nothing but you want to maximize the likelihood of your data, right? Like which is nothing but, or log likelihood of the data, which is nothing but this probability distribution, right? That's what fine tuning is about. Yeah, so you are given these models, and then, okay, so let's look at what's happening with the prefix thing. So the prefix itself would be mapping to some prefix indices, just like words. And let's say this is the length of the prefix. So these prefixes can be in form of a matrix, where each row is one prefix vector, just like a dictionary thing. Right, so then, what you do is, you're given this prefix matrix now, and the activation will now depend on if your index is within the prefix matrix, sequence of prefix indices, then its activation is going to be nothing but a row from this prefix matrix. Otherwise, at higher layers, it's going to be the output of the LM, right? And then you have the same likelihood loss. So what you're doing is, your prefix, actually what happens is, in prefix matrix itself is reparameterized. So what it means is, like, this is done to have stability in the model. So what you do is, like, you have some prefix vector, let's say here, you pass it through a MLP, and then get a new prefix vector which is concatenated with the key and the values, and then the self-attention and everything happens. And the reason this is done is it brings in more stability. Otherwise, if you just directly use this prefix vector here, it doesn't train well, and it's not stable. So you add this, because it could be the case that this k is in some space, and the prefix vector that you have attached may not align with that space, and then there would be some sort of misalignment, and it may not lead to a stable training. So this MLP helps to map it to a space which will help in training, basically. Is this clear? Like, and during inference, what you do is just, you have already trained this neural network. So what you do is, you just directly use the prefix vector, which is the output of the neural network. You attach it to the key and the value, because it's already trained now. So you just have to do the inference now, right? So this is how this prefix tuning basically works. So is this clear? Any questions on this? All right, so maybe I'll skip the experiments and the results that have been done on these in the interest of time. But let me just assure you that prefix tuning works, and it gives better results than many of the other things like adapters, which we are going to look later, right? And the good thing is that prefix, with just 0.1% of the task-specific parameters, it's much better than some of the other techniques which might be using almost like 3% of the total number of parameters, right? And maybe I'll skip this. And also another interesting thing is that prefix tuning outperforms the full fine tuning in low data regime. When you have less amount of data, prefix tuning works much better. Like this orange line which you see, it's always up. If you have less data, then its performance is much better than the full fine tuning in same low data regime. Right? Maybe so the another interesting thing is that prefix tuning, so actually no one asked me this question, like what should be the number of prefixes or number of prefix tokens that should be attached. So what happens is, like, you can keep on increasing the prefix tokens till a point the performance keeps improving, but after a while it starts degrading. So can anyone guess why this happens? What could be the possible reason that it starts degrading? Sorry?
The context window? Or?
No, not really. Even within the context window, still it starts degrading. So possibly what is happening is there's some sort of overfitting which is happening. So during training, you have some specific prefix length, and if that length is too big, then the model would already overfit to that thing, and during testing, obviously that will result in poor performance. Right, and also one more thing, another interesting thing is that you can apply this prefix tuning at different layers of the transformer, right? Like what I showed was only at the input side, but no one stops you from applying it at different layers. And what is observed is that in general, the performance drops. If you go to higher layers, that performance is dropping. Or if the Wait, this is, So the thing is that if you do it only at the embedding level, then the performance is not that big. If you apply it somewhere in the middle, then it slightly improves. And you can also try different kind of things, like you can apply prefix, you can apply infix, but in general prefix works better than infix. Another thing is that these prefix vectors that you are doing, you are randomly initializing. You can be smart about it. Like what you can do is initialize them with the embedding of the of a word which is related to a task. So suppose you want to do summarization, if you initialize with the word, the embedding of summarize, then the performance is much better. Right, so that's what has been observed. Yeah, so to conclude this part, like prefix tuning is, I mean, a good lightweight alternative to full fine tuning with much less parameters and much more efficient, and it supports like personalization and mixed task batching. So the next I will go to the adapters. So I'm sort of out of time, but I mean I still have two things to cover. What shall we do? Okay, so okay, yeah. Okay, so maybe so some of these things will be covered in the lab also, that we can do. But maybe let me quickly tell you what the main idea behind adapters. So in adapters, what you do is so this let me just, this one slide will tell you what adapters do actually. So what you do is in adapters is, like, let's say you have a transformer layer. What you do is you plug in a small neural network or small sub network between the transformer layer itself. Right, so what you have is an adapter layer, and this adapter layer is like sort of a bottleneck layer. What you do is this will take some input, project it to a smaller dimension, and then reproject it to a higher dimension. So you plug in these adapter layers within the transformer layer, transformer block. So you have this before the residual addition and before the layer normalization, and another adapter added here. So that's how the adapter is basically. Right, so maybe I will skip many of these details, and I mean I'm skipping the details, but I mean it works basically. I mean, let me just put it in one line, that works. Right, and then the last one is LoRa, or low rank approximation. The idea is also quite simple here. So I guess every one of you knows singular value decomposition, right? You factorize a matrix into these orthogonal matrices U and V, right, with a singular diagonal matrix, right? And also the SVD K, which is like the kth approximation of SVD, right, where you sort of prune smaller singular values and only consider something which are above certain threshold. So what you do in LoRa is something really simple. So you have these pre-trained weights, right? How do you update the weights is, the way the weights are updated is W0 plus some delta W. So what you do is, you just factorize this delta W into two matrices, B and A. And these are low rank matrices. And now during training, you only update these are frozen, and only you update these weights. But one thing that you need to be sure is that these, at the beginning of training, these should collapse to the original, I mean this thing should be 0 essentially, right? Because at the beginning of training there is no weight update. So for that, what you do is, you can select A matrix by sampling from a Gaussian, but the B matrix has to be 0. Then only the product is going to be 0. Right, so, and that actually brings stability in the training. Otherwise, it might just become very unstable during training. Right, so that's essentially it, basically. That's what LoRa is. I mean, how do you decide this rank and all those things? Those are sort of a bit more details, which can be, so essentially this is what you are doing. You have this weight update, you approximate the update itself by product of two small low rank matrices, and then you update using this. And let me just tell you one important thing. Yeah, and it works basically, I mean, just believe me. And so what also has been observed is like this R rank, which I was telling, the smaller rank that you're approximating it to, what is observed, like let's say you have a rank 64 and a rank 32. What is observed, like the rank 32 matrix is actually subsumed in the rank 64 matrix. That's what they have observed. I mean, it's within the subspace of the larger matrix, right? And the other thing is the weight matrix that you are updating, the delta W has a strong correlation with W. And in fact, what is happening is this delta W is amplifying the directions that were not emphasized in W. So see, as I said, all these large language models are like black holes. They have everything that is there in this universe. It's just matter of like triggering those. So something similar is happening here. The weight matrix has that information, but it's sort of subsided. But these updates actually amplify that part of the weight matrix which will help in solving the task. So that's what is happening. I'm skipping a lot of details, but I mean they have shown by calculating the projection of those delta W onto the weight matrix to see what's the overlap there. So they see certain directions are getting amplified which were not big enough or in the original weight matrix. Yeah, so that's the LoRa, and yeah, I think maybe I'll conclude here given the interest of time. So yeah, we saw that, I mean, we cannot fine tune the entire models. These are huge in size. So what you do is usually use some sort of PEFT, and we looked at 3 prominent techniques of prompting, adapters, and LoRa. And there are lots of different PEFT techniques. I mean, I cannot go into details of each of them, but the 3 techniques I talked about are like the sort of genesis of all the other PEFT techniques that are there. Right, and now we want to go into hands-on tutorial. I'll just share the link with you, and maybe I'll conclude there. And many of you were asking me about like contacting me. So if you want to contact, please feel to reach out to me over email. And I have a lot of openings. So if any one of you is interested, please feel free to contact me. Thanks a lot. Yes. So yeah, maybe I will just quickly go to the tutorial. Yeah, so you can, oh, I cannot share this screen. Oh. So, okay, so link, wait, I'll share the link first. If you can just go to this link, it's quite easy, tinyurl.com/peft-tutorial. Just go to this link. Maybe you can switch on the lights now, or maybe open the door. I can. The link has been shared. Okay, okay. So everyone has the link. Does anyone is there who doesn't have the link?
The link is there at the WhatsApp group. It has been sent, I think, a few minutes ago by our again. So can you please send it? Do you have any questions before that?
Yeah, oh yeah, by the way, any questions so far? I forgot to ask. Sorry, I could not go into too much details in the interest of time, but I mean, hopefully in the tutorial you will be able to explore all these things. Large concept model?
Yes.
What is large concept model? Actually, I don't know what is large concept model.
Recently, there is a new, should I say new version of large language models? So it's called large concept models. I thought.
Okay, sorry, I am not aware of these large concept model.
Okay, besides that, when we go back to the techniques, we talked of one was scaling, and you mentioned the 2 different ways of scaling. That was the KM scaling and the
Chinchilla, yeah.
Chinchilla scaling. So, amongst the 2, which one do you recommend and which one works best?
Yeah, so that's a good question. Actually, there's no, see, there are 2 different perspectives of the sort of similar phenomena. So some people have used KM's Kaplan or the KM scaling, and I think in Llama they use KM scaling. And DeepMind people tend to use Chinchilla scaling, or Google people tend to use Chinchilla scaling because obviously they have proposed it. So, but essentially both of them are talking about the similar thing, except the constants are different there. So, I mean, I mean, I would suggest maybe you should go for KM scaling because it has been tried by a lot of people, and like GPT guys have tried it, and then Llama guys have tried it, so that has worked out well. So yeah, I mean, I would suggest you can start with KM scaling.
Okay, thanks.
Yeah, so in this tutorial, basically this is about PEFT, right? So here you have to work on, I mean, first you will fine tune the model to see what's the best performance that you, so okay, let me talk about the task that you have. It's, I think, yeah, so you'll be using T5 model, which is the encoder decoder model, and you'll be using IMDb dataset, which is for sentiment prediction for a review. So what will the sequence is like this: you will fine tune the model and see what's the best performance that you can get, and then you will try different prompting different PEF techniques to achieve similar performance, like soft prompting, then adapter based prompting, and then LoRa, right? And so those things you can try, and actually the tutorial is sort of more or less self-explanatory. I mean, you can just keep walking through step by step and most of the things would be clear. And there, like in, you'll have to fill in few things which is part of the lab, which like for example, like if I go to, let me go to soft prompting. Yeah, here like soft prompting, you have to, yeah, so you'll have to put in your code here. I've put the comment there, put your code. So that's what the lab is about, like, and which is about, like, in this case you have to write the training loop essentially, right? And similarly other, I mean, I've put the things at other places also, right? So maybe, I mean, I will keep it sort of informal. You can start working on this thing, and there are TAs who can help you out with this thing. Thank you. Yeah, so I'm Ashutosh. So I am a professor at IIT Kanpur. So I'm coming from India, and I'm in the computer science department there. And my main research area is NLP and machine learning, and that's what I research in, and I also teach subjects in this area. Yeah, so it's I'm sort of a regular speaker here. I've been coming here since 2019, and it's always really fun, so much fun to come here and interact with students. Students are really good here. I always enjoy giving lecture to them, and then their questions are really interesting. Enjoy talking to them, and also, I mean, Nami has been doing really great job, and I always want to help them. And like Bishesh and Binod are really good friends with me, and I always look forward to helping them and promote specifically like AI education in Nepal, and that's one of my motivation of coming here, and really enjoy the time here. Thanks.